So we're going to continue by talking about types of energy and types of work. So the three types of energy that we're going to be talking about today is spring potential energy, kinetic energy, and gravitational potential energy. There are other kinds, but these are the three that we're going to care about. And then there's types of work. You can either have work from a push or pull, or you can have work due to friction. So when we're comparing these, we want to think about impulse and work. So to change the amount of momentum, you needed to apply an impulse. And that impulse was a force times the time. So to compare this, for energy, you need to do work to change the amount of energy. And for work, it's your force times your distance. So this is very similar here. You have force times time, and for energy or work, you're going to have force times distance. So let's look at this. All right, so for impulse, this is going to be your change in momentum compared to work, which is your change in energy. Either one of these can change the amount of velocity that an object has. So momentum is mass times velocity, and then depending on what kind of energy it is, it could make it speed up or slow down. Then over here we have the equations. So impulse is force times time, and work is force times distance. So these are very similar. In either case, you need a force to cause either an impulse or amount of work done. The variable here is J for impulse, and the variable over here is W for work. And then we can look at our units. So the units for impulse is newtons times seconds, and then the units for work is joules. So joules are equal to newtons times meters. And then here we have both of them are going to have both a magnitude and a direction, so they're a vector, because the direction that your force is going in does matter. And then impulse is the area under a force versus time graph, and work is the area under a force versus distance graph. So work is equal to your change in energy, and positive work is going to add energy to the system, and negative work is going to remove energy from the system. And the equation for work is that work is equal to force times distance. And this is when the force is constant and in the same direction as the displacement. So when I'm pushing on something, the force and distance are parallel to each other. I want to make this point here, though, that work is equal to force times distance and torque is equal to force times distance, because students oftentimes get this very confused. Here, for work, the force and distance are in the same direction or they're parallel to each other. And when we're talking about force and causing something to rotate, your force and distance are perpendicular to each other. So just be careful about that. So we're going to talk about three kinds of forces. We're going to look at work done by a constant force or friction, work done by a spring, and work done by gravity on an object far from Earth. This is the equation for work. So if you take calculus, this is what it'll look like. The idea is that your amount of work done is going to be equal to, when you go from point A to point B, that force that you're exerting times, and then this is going to be like how far you go. So if you have a constant force, the area underneath this graph is going to be how much work is done. So before, when we were talking about impulse, it was force and time. Now we're talking about work, so it's force and distance. So it's very similar but different. And this work is equal to your change in energy. Therefore, the area under this graph is also going to be the change in energy. So now the second one that we're going to talk about is work done by a spring. So the more you stretch a spring, the bigger the force it's going to take. So if you've ever tried to squish the spring in a pen, you'll notice that as you start to squish it, it squishes really easy. And the more you push on it and the more it's compressed, the bigger the force you need to hold it there. Um, and a spring that follows this kind of graph exactly is going to be a spring that follows Hooke's law. So Hooke's law says that your force is proportionate to the spring constant times how far the spring is stretched. So the force of the spring is Fs. Your spring constant is going to be how stretchy or stiff or hard it is to stretch the spring. So for example, if I take and I have a little spring from a pen, it's fairly easy to squish. If I take the spring that is in your garage door, that spring is really, really hard to stretch. And so the number that tells you just how hard it is to stretch or squish a spring is the K. And then this X is going to be how much the spring is stretched from equilibrium. And what that means is this, like if I take this and I just hang it here, and then I pull it down some more. So now my spring is this long. The distance X is the difference between when I was not squishing it and when I'm squishing it now. So this distance from here to there, this is my weight. That's not the spring. That's going to be my X. So it's, if this is not squished or not stretched, and then this is all the way stretched, the X is the difference between the two. So if I go ahead and I graph my force versus distance graph for a spring, I know that the force of a spring is going to be my spring constant times the distance that it's stretched. And I know that the area underneath this graph is equal to the work done. And it's a triangle, so that means it's 1/2 times my base, which is d, times my height, which is f. So if I take this kx and I plug it in for my force, then I'm going to end up with work is equal to 1/2 times kx times the distance that it was squished, which is going to be x. So if I go ahead and I multiply this out, I have the 1/2 times k times x, which is going to be, which will give me 1/2 kx squared. This work done when you stretch a spring then is going to be equal to my spring potential energy, or the energy stored in a spring. So down here at the bottom, I know that energy is equal to how much work is done. Therefore, the spring energy is going to be 1/2 kx squared. So this is one of the equations that you're going to be using quite a bit in this unit, and you'll either want to make sure it's easily accessible or memorized. It is on your equation sheet. When you're talking about work done by gravity for something that's far away from the surface of the Earth, the closer you are to the planet or the sun or whatever it is that you're talking about, the bigger the force is going to be. And as you get farther and farther away, the force is going to be smaller and smaller. So if I were to find the work done here, between these two distances, I would need to find the area of that. But we will get back to this a little bit later. But for right now, all you need to know is that it's a graph that looks kind of like this, and the area is equal to the work done. So, a couple other things to know about work. The first is that you must exert a force over a distance. So, if you're doing work, it's your force times distance. If the distance that you make something move is zero, then whatever your force is times a distance of zero is just going to give you work of zero. So, in this case, the con may expend energy when he pushes on the wall, but if it doesn't move, then no work is performed on the wall. This kind of concept is very likely to show up on a test. So you'll want to remember that you need that displacement to have any work. And then the other thing to know about work is that your force must be in the same direction as the movement. If it isn't, then you have to use a vector component of that force that is in the same direction. So in this case, my lawnmower is moving to the right. Therefore, I need to know how much force is going to the right. So if I'm pushing down on the lawnmower at some angle here, I need to find how much of that force is going in the same direction as I'm pushing the lawnmower. So in this case, I would write it as my work is equal to force times distance, and my force would be F cosine theta times the distance, which would just be the little d. And then next, what we're going to talk about is the three types of energy.